Hello everyone, my name is Ed Ryan. I'm a Knowledge Transfer Partnership Associate working with the University of Manchester and Arrow Global. In this talk I will describe efficient Monte Carlo methods for forecasting returns from consumer debt portfolios. So a little bit about the company in this Knowledge Transfer Partnership. Founded in 2005, Arrow's core business involves buying defaulted debt. This debt it buys from banks, credit card companies and other financial institutions. In the UK, the debt it purchases is primarily consumer credit, which has much greater consumer protection compared to other kinds of debt. For example, council tax debt. And in particular, after default, no interest is added to the debt. This is in contrast to something like council tax debt, where interest can be added. Arrow is regulated by the Financial Conduct Authority. This is significant because it means that Arrow must treat customers fairly. It uses a model to forecast estimated remaining collections for around 6 million customers over the next 7 years. So this estimated remaining collections are needed for the valuation of the assets on the balance sheet and for deciding on different strategies for different customers. The model consists of 3 for loops. They are for the number of realizations, number of quarters, and the in the simulation, and the number of accounts. The third for loop can be parallelized because of the particular programming language that we use. And after the model is finished running, we sum the account level collections across time and then take the mean of the 7-year collections across the number of realizations. There's 2 main aims to our Knowledge Transfer Partnership project: to improve the accuracy and computational efficiency of forecasts from this estimated remaining collections model. And we'll do that in 2 ways. By varying the number of realizations for different accounts, in contrast with the current setup where the number of realizations is the same for every account. And then using stratified sampling. And the second main aim is to incorporate uncertainty on the forecasts. In this talk, I'm just going to be focusing on the first aim. Due to the commercial sensitivity of the ERC model, I can't describe the specifics of the model. However, I can describe a toy model, which can give you some idea of the mechanics of this ERC model. So for a particular time point, we compute the probability that the customer will pay, where the probability of paying is computed using logistic regression. We then generate a random number called U1. We also generate a second random number, but this is used in the next slide. So for this random number U1, this is compared with PPay to determine whether or not the account will pay for the particular time step. Like the ERC model, this toy model is also stochastic. So this is achieved by generating a random number U1 for each of the realizations, and then it's also separate for the account and also for the particular time step. We then compute the probability of settling. So this is assuming that the person is paying. We need to know whether they are going to make an arrangement or make a settlement. Now in the ERC model, the probability of settling is another logistic regression equation, but here in this toy model we just fix it at 0.5%. Then our second random number U2 is compared with probability of settling, and then this determines whether or not, as I said, the customer who's paying will make a settlement. That means paying off the debt, or whether they'll make an arrangement, which means setting up some kind of monthly payment, monthly or quarterly payment plan, such as a direct debit. The probability of paying is a function of credit score and pay history. So this variable pay hist is the number of months the customer has paid prior to the previous month. And the never, ever, and paying are different types of ERC status. So never means that prior to the previous month, the customer never paid. Ever means that they haven't paid in the previous month, but have paid at least once prior to that. And paying means that the customer paid in the previous month. So I'm going to demonstrate how the toy model works by simulating the balances of 4 synthetic accounts. So although the model simulates collections, from a visualization point of view, it's helpful to show the account balance, which obviously goes down for each month that the account pays. And I'm going to show this for 5 realizations for each account. So as you expect, the paying account with good payment history has a balance that decreases the fastest, whereas the balances for the other accounts decrease slower. You'll also notice that there's a sudden drop in the yellow line. This occurs because one of the realizations, in one of the realizations the account settled, but it didn't for the other realizations. And that's a consequence of only having 5 realizations in total. So now when we do the same thing, but we have 100 model realizations, we'll see something a bit different. But just before I press play, I just want to point out that the evolution of the balances in this video is not a reflection of how fast the model runs. Each of these 2 videos is just a composite of lots of JPEG files that show the balances at different time points. So now with 100 model realizations, you'll notice the same order in which the balances decrease according to the account type. But here you'll notice that the lines are all a lot smoother. So this is because, for example, if one of the realizations, if the account settles for one of the realizations but not for the others, then a large number of realizations means that this difference is smoothed out more. So this is great. It's good to have lots of realization, but there's something more fundamental about increasing number of realizations, and that is that we can reduce the Monte Carlo error. However, there is a slight problem. And the problem is that if you, how do you reduce the Monte Carlo error of the ERC model forecasts without increasing the computation cost of running the model? Because obviously if you have more realizations, that's extra cost in terms of actually running the actual model itself. So how do you get around this? And so this is now we come to the first aim of our project. So we're going to vary the number of realizations for different accounts. So let me just demonstrate this using a simple example. Suppose we have a portfolio with 2 accounts where X1 and X2 are random variables that represent the forecasted 7-year total collections of these accounts. And let's suppose that these 2 random variables are normally distributed, and one has a variance of 0.01 and the other has a variance of 100. Then the portfolio level collections are defined by the sum of these 2 accounts. So let's let xi, k, denote the kth realization of xi. And suppose our goal is to estimate the expected total collections given by mu t. Then an unbiased estimator for mu t is this, and this is just simply for each of the 2 accounts we take the average across the realizations and then we add that together. And hence from this we can work out the variance of this estimator, and then when we substitute in the variances we have, which we defined, then we get this formula to the right. So just kind of summarizing what we've got, this is the formula for the variance of mu hat. Now in the current setup we use the same number of realizations for each of the 2 accounts. So I'm just going to keep it general. Let's suppose we call it n. So n here could be 5, could be 10, could be 20, could be 50, whatever, but it has to be the same number of realizations. Now an efficient allocation of resources would realize that the variance of the collections for the first account is a lot smaller than the second one. So therefore we only really need one. The best way to allocate the resources would be to give one of the realizations to the first account and give the remaining 2n-1 to the second account. And so then when you substitute those into the formula, you get this. And what you find is that this will always be smaller for integers n greater than 1. So that's fine for just 2 accounts, but in general we have more than 2 accounts. So let's call it capital N accounts, and we run the ith account through the ERC model Ri number of times, where xi is the 7-year collections for that ith account. So the variance of bu hat is given by the sum of the variance of xi over Ri. We add up t is defined as the total collections across all of the accounts, and our estimator mu hat is given by this. It's just an extension from 2 accounts to n accounts. So our optimization problem, now the point in the previous example, it was fairly straightforward to recognize you have 1 and then 2n minus 1 accounts. But it's not so obvious when you have more than 2 accounts how you should allocate your resources, which account should have, how you should divide the total number of realizations amongst the accounts. So our optimization problem is, given a fixed computational cost and assuming that the variance of xi, our variance of collections for all I are known, we need to find the optimal value of Ri such that the mean squared error of our estimator is minimized. So we do this by using Lagrangian multipliers, and this is the setup for this particular problem. And we differentiate this with respect to Ri. We set it to 0 and we solve. And we also use the equation for the cost, C. And those 2 equations then allow us to eliminate lambda, and we get the formula for Ri. So this gives you the formula for the optimal number of realizations for ith account. Now, I said in the previous slide, assuming that we know the variance of xi. Now, what I mean by this is the true variance, as in if you were to do lots and lots of realizations, like thousands of realizations, what would the variance of the collections be? Now, this is obviously not possible to do because we are limited by the number of realizations. So what we do is we build a Gaussian process emulator, and then we use the emulator to predict, given some account characteristics that we know, what the variance of the collections should be. But to build the emulator, we first need to create synthetic accounts using maximum Latin hypercube design. And the reason why we use synthetic accounts, not real accounts, is because we need to choose the design points so that they are as space filling as possible, and that would be very difficult, if not impossible, to do with real accounts. We then run the synthetic accounts through the ERC model for 5,000 repeats, and then we train a Gaussian process emulator using the synthetic data. Now, the good thing about the emulator compared to other types of surrogate models is that you don't need a lot of training data. For us, we just needed a few thousand accounts to train the emulator. This means that running each of these accounts 5,000 times is not computationally expensive, since a few thousand accounts is just a tiny fraction of the 6 million accounts that are put through the ERC model for the actual kind of simulation forecast. The Gaussian process emulators were traditionally used to approximate the input-output relationship of deterministic models, which means that for a given input you always get the same output. But in our case, the variance of the collections for 5,000 realizations, although it's close to being deterministic, there is still some stochastic behavior. So as a result, we need to include a nugget term in the emulator to take account of this. Next, we need to validate the emulator using other synthetic data, and we use a leave one out approach, and this based on the paper by Bastos and O'Hagan from 2009. And this validation is really important because if the validation diagnostic checks fail, it means that our emulator is not a realistic representation of the input-output relationship of our model, of our expensive model. So we shouldn't use the emulator. So it's really important that we make sure that the emulators are good. This This paper, if you're interested in looking it up, the title of it is called the Diagnostics for Gaussian Process Emulators. And then finally, we apply the emulator using real accounts in order to compute the variance of the collections for each account. So to train the emulator, we need a set of inputs and outputs from the ERC model. The inputs correspond to 16 account characteristics, and the outputs are the variance of collections after running these accounts through the ERC model for 5,000 realizations. So the numbers you see here are not from real accounts. These are just to visualize the structure of the inputs and outputs. So validating the inputs, validating the emulator, there are three main validation diagnostics checks that we can carry out. And the first, we compare the emulator predictions of the variance of the collections with what we should get from the ERC model. And you can see here we have an R-squared of 0.86, which is good, but it's not, definitely could be improved. But this doesn't take into account the emulator uncertainty, so we can take that into account by looking at the prediction error. And as you can see, the proportion of points outside the 1.96 to 1.96 range is 7%. Ideally, this would be 5% or less, but I don't think that's large enough in order to give us a reason to throw out the emulator. Now, the final diagnostic is to calculate the Mahalanobis distance, and this takes into account the correlation between the validation data. So up until this point, I've just been referring to a single emulator, but in fact, we trained 11 different emulators. This is because for different operational segments and ERC statuses, different numbers of input variables are required. So the segment or operational segment here refers to the way in which the accounts are grouped for operational reasons. So for example, segment 1 never accounts, there are only 11 input variables, but for segment 1 ever accounts, there are 16 variables. So that's why we need to use different emulators. So for the Mahalanobis distance, for this check to be to kind of pass, we want the triangle to lie within the error bars that denote the 95% credible intervals of the theoretical distribution. And as we can see, for 9 of the emulators, this is true or almost true, but for 2 of the emulators given by red, we can see that the observed Mahalanobis distance is a long way from the theoretical distribution. So for the segment 4 accounts, we did not use the emulators when determining the optimal number of realizations. It means that we would need to try a different approach to estimating the optimal number of realizations for those accounts, for those segment 4 accounts. But for the remaining ones, we can use the emulator. And so once we have estimated the variance of the collections for those accounts, we can then plug that into the formula to determine the optimal number of realizations. And that's given by the red, blue, and green lines here. The dashed black line represents the current setup where the number of realizations is fixed, or it's the same. So it's fixed at a specific number for all of the accounts. You'll see for the never accounts, so given in this top plot, that most of the accounts need fewer than the specified number from their current setup. And this makes sense because never accounts, remember, are accounts that have never paid prior to the simulation run, and therefore the likelihood of them paying is throughout the 7-year forecast is quite small. So we would then expect the variance for a lot of these accounts to be quite small. For the ever and paying accounts, we see a higher proportion that need more realizations than the specified number from the current setup. And this also makes sense because these are generally paying accounts. They are accounts that have paid at least once in the past or are paying currently. That means there's more variation in the payment behavior, and that's going to lead to a higher variance. Overall, we see a 70% reduction in the variance of our unbiased estimator, in the variance of our unbiased estimate of the total collections across all accounts when we adopt this optimized setup. And so this is a very significant reduction, and this is really good to see. And although this reduction in the variance of MUHAT was a lot, we next explored whether or not using stratified sampling could reduce this even more. And the basic idea is that there may be similar behavior in many of the accounts, and therefore it might make sense to group the accounts. So the key idea here is for the stratified random sampling with replacement, we group the accounts that have somewhat measure of similarity. So for example, group 1 could be accounts that have low forecasted collections. So the 7-year collections in each of these accounts are very similar to one another. And then maybe other groups might have other similar characteristics. And the point of this is that it's stratified random sampling. So we're not running the model for all of the accounts. We're only running it for a sample within each group. And because we're only running it for a sample and not all of the accounts, this allows us to run more realizations for the accounts that need it. The accounts that have a higher variance, we can run more realizations for those accounts. So one way of grouping them is by operational segment and the ERC status at the start of the simulation. So as you can see here, we plot the expected 7-year collections alongside the variance of the collections for each of the accounts. And you can see that so this would be a good one way of grouping the accounts, 9 different groups here. But we could further subdivide each of these groups. For example, the never accounts in segment 1, we could split this into 2 more groups, one that has a lower variance and then one that has a higher variance, and then we could even subdivide even more beyond that. So there's ways in which we can group the accounts and have lots of groups. So what's the math behind this? Well, from the no sampling setup, and sorry, I should say the no sampling optimized setup, these were the equations and formulae that we used. And with the stratified sampling setup, our estimator is given by this expression here. Now, xi before referred to the 7-year collections for the ith account, but here we're doing sampling. So we create a new random variable y, and ygjk refers to the jth sampled member and with replacement of group G from the kth realization. Okay, and we use Lagrangian multipliers once again, and this gives us the optimal value of mg times rg. Now mg here refers to the number of sampled members within group G, and RG refers to the number of realizations of those sampled members. We are currently, the work I just mentioned in the last slide is ongoing, so I don't have at the moment results to show, but one of the things we're trying to figure out right now is to determine the optimal way of grouping the accounts. So for example, well, there's two aspects. It's how you should decide on the groups, like what criteria you should use, and also how many groups is optimal. So for example, if you have a portfolio consisting of 50,000 accounts, is it better to have 100 groups or 1,000 groups? We're also, beyond this stratified sampling method, we're looking at and investigating other methods for reducing the Monte Carlo error. And finally, this wasn't part of this talk, but I mentioned it in the aims, the second aim being to quantify the uncertainty on our forecast. And this is critical, because when we make decisions based on these forecasts, if the uncertainty is too large, then that will affect what decisions that are made on those accounts or on those forecasts. Thank you very much for listening, and I'll be very happy to answer any questions that you have.